Hi and welcome back. So today we're going to be looking at calorimetry, which is applying what we've learned about fuels, thermochemical equations, and now looking at them in terms of an experimental context. So let's get started. So simple calorimetry is essentially an experiment where we burn a fuel and we heat water and then measure the change in temperature of the water. This allows us to measure the heat of combustion of a reaction using very simple apparatus. Okay, so you can see here we have a copper tin, which is highly conductive, which will be absorbing the heat and passing it through to the water that is inside from the spirit burner down below. So if we burn a fuel under a known amount of water, i.e. we know the mass of the water, okay, we can measure the initial temperature and the final temperature and use Q equals mc delta T in order to be able to work out the heat energy that passed from the burning of the fuel into the water. Okay, so this process is known as calorimetry. The calor at the front here, this is from calorie, which is our old unit of energy. Okay, and then derimetry is the method or process of measuring. So this means that we need to recall some of our information from year 11, in particular, the information about specific heat capacity. So you'll remember that we have the Q equals mc delta T equation. Most importantly, this will produce our heat in joules. So we need to remember that there's probably going to be a conversion if we're looking at heat of combustion, because that is usually given in kilojoules per mole. So we need to remember that this is in joules when we do it this way. The heat capacity of water is given in our data booklet and is 4.18 joules per gram per degree C. Mass will be of the solution being heated. Okay, so this will typically be the water, and then delta T is our change in temperature. So this means that using this, as long as we know the mass of the water, which we can get by the idea that 1 milliliter of water is equal to 0.997 grams, also in your data booklet if you have forgotten this, and different to the one that we commonly used in year 11 where we said it was 1 gram. So if we do this, we can measure the change in temperature of the water or any other substance that we're heating up and determine the amount of energy that it absorbed. So this is the experimental setup. You'll see here that we have a thermometer that is testing the temperature of the solution. There's recommended to have a lid here, okay? The metal container clamp, water. This is a heat shield or a reflective heat shield that allows the heat energy that is being radiated out to reflect some of it back in. Okay, if you remember when we talked about our power stations, we said that the most of the energy is heat lost to the surroundings was one of our greatest inefficiencies. And the same goes for this kind of experiment. As you can imagine, we have radiant heat emanating from the flame here, so we're going to be losing that. It won't be transferring directly into the water. The lid is to stop heat radiating out the top. Okay, and then this reflective shield is to minimize the heat loss to the surroundings as well. Okay, then there's the wick, the spirit burner, and everything else. So you can see with this, there are different ways that we could minimize heat loss from the environment when doing an experiment. Quite often you will see that the experiment is run without a shield and sometimes even without a lid. So these would be improvements that you could suggest to any setup that didn't have these two things here. These improvements would allow us to have less heat loss to the environment, increasing the accuracy of our result. So insulation, if we can insulate our container, it means we will minimize heat loss to the surroundings and get a more accurate result. We do need to have a known volume of water and the reactant at the beginning and the end, okay, in order to get an accurate mass. okay, a known temperature of the water at the beginning and the end. Once we have these out, we can again remember Q equals mc delta T, and we have all the information that we need for this. It is critical to remember that there will be some assumptions being made in here. Generally, we will assume that the density of the aqueous solution, if it is a reaction that's occurring, an exothermic reaction that occurs in solution, is equal to the density of water. Okay, and this is, of course, our 0.997 grams per milliliter for our density of water. Let's have a look at a couple of example questions. In this one, we've been told that we have 0.295 grams of ethanol that is undergoing complete combustion. This is in a spirit burner, so it's in the bit underneath. It is the fuel that's being burnt, and the heat energy is released to heat 100 milliliters of water. Okay, so that is going to be what's in our tin. Okay, and the temperature of the water rose from 19.56 to 38.85 degrees. We're asked to calculate the heat of combustion, remembering that delta HC is equal to energy divided by N, and then Q in this case is going to be equal to our energy, which is going to be equal to mc delta T. So if we have a look, we want to find the mass of the water because this is what is being heated. So this is going to be 100 multiplied by 0.997. Okay, C is 4.18 from our data booklet, and then delta T is going to be 38.85 minus 19.56. Okay, if we add all of this into our calculator, we will be able to calculate the energy, and remember that energy is in joules. Okay, hopefully you put that into your calculator and you came up with a total of 8,039.03 joules. Okay, now remembering that energy must be in kilojoules when we work out delta H. So our energy for this equation is going to be 8.039 kilojoules. Then we need to work out our number of mole of ethanol because that is the fuel that we burnt. So in this case, we're going to have 0.295 divided by the molar mass of ethanol, which is going to be 2 times 12 plus 6 plus 16. So that's going to be 46 grams per mole. That's going to give us a total of 0.295 divided by 46 is 0.00641 mole. So now, in order to work out the energy, the enthalpy of combustion, we are going to take 8.039 divided by 0.00641, which will give us 8.039 divided by 0.00641 is going to give us 1,254.13 kilojoules per mole. Double check our number of significant figures. It should be 3. So we're going to get 1.25 times 10 to the 123 kilojoules per mole in the correct number of significant figures. And that's the process that we use from burning a fuel, heating the water using Q equals mc delta T, and then dividing that by the number of mole that was burnt in order to find the heat of combustion. You could then write your thermochemical equation by writing the complete combustion reaction for ethanol, and of course using this value here as your delta H. Again, we've got a few more problems. So with each one of these, pause the video, have a go at calculating it, and then come back to look at the answer. In this case, we have a spirit burner being filled with methanol. they have measured the mass before and after in terms of working out how much fuel was burnt. It was lit, and then they allowed the temperature to rise by 20 degrees. Okay, so in this case, this is going to be your delta T. The flame was snuffed out, final mass of the spirit burner and methanol was measured, and the results are shown below. So this gives us, from here, the difference here will give us the mass of methanol. Okay, we have our temperature, water in the can. They said approximately 20 degrees, but we can see here that it's actually, delta T is going to be 24 degrees. And then don't forget our volume here. So we've been asked to determine the heat energy change during this experiment and the heat of combustion of methanol. So first step, you're going to use Q equals mc delta T to find out the amount of heat energy. Then second step, you're going to do delta H C is equal to energy divided by N, remembering to make sure that your energy is in kilojoules before you do this calculation. So pause the video here, have a go, and come back to see the answer. Okay, so hopefully you worked out that we had 20 kilojoules of energy that was absorbed by the 200 mils of water. So remembering that we had to have 200 up here. Then working out the number of mole of methanol, we have the change in mass divided by 36, which is the molar mass of methanol, gives us 0.0625 mole. And from there, we can work out delta HC by taking our 20 kilojoules and dividing by the number of mole. You can note I did my conversion to kilojoules up here before substituting into the delta HC equation. So we can use the delta H values given in thermochemical equations to work out the amount of energy released or absorbed in a reaction based on the amount of reactants or products in stoichiometry. And we've talked about this in class already. So we can answer all sorts of questions now by having a experimentally determined value, which we can compare to the theoretical value using the theoretical enthalpies of combustion that are listed in our data book. So we can also look at examples of these to work out the number of mole that would have been burnt or used, etc. So if we look at this one, we're asked what mass of propanol. So remember, this is a 3-carbon alcohol. Okay, so we're going to have CH3, CH2, CH2OH. Okay, for propanol. This, we don't know what isomer we would have. So the best way to do this is to look at our molecular formula when writing the equation of this. It's burnt in excess air, so this is telling us that there is excess oxygen, so we're looking at complete combustion, and we are told it produces this amount of energy. So if we have a look here, we have the balanced thermochemical equation for 2 mole. We are producing this amount. So from the equation, delta HC is going to be equal to negative 4034 divided by 2, because we want to work out per 1 mole. So 4034 divided by 2 is going to be 2017 kilojoules per mole for delta HC. Now we need to work out the mass of propanol that must be burnt in excess air. So we know that delta HC is equal to E on N. So we have delta HC, we have E, so we need to find N. So let's rearrange. N is going to be equal to our energy divided by delta HC. So 1.00 times 10 to the 4 divided by 2017. Okay, so 1.00 times 10 to the 4 and dividing that by 2017 gives us 4.958 mole of propanol. So now in order to work out the mass we're going to use our number of mole is equal to m on mr. So rearranging this, we get mass is equal to n times mr, which is going to be n, 4.958, multiplied by the molar mass, which is going to be 3 times 12 plus 7 plus, that's going to be 8 plus 16. So 36, 44, 60. So we're going to have 4.958 times 60 grams per mole. It's going to be 297.48 grams of propanol would be required in order to burn that for that amount of energy. Okay, so for this, we've used a combination of our delta HC, our delta HC equation in terms of energy divided by number of mole, and then just the mole equation that we were introduced to in year 11. Okay, I want you to have a go at this equation. This is one based on ethane, so remembering this has the double bond, triple bond CH, triple bond CH. Okay, and we're given the complete combustion of 8.55 grams to produce this amount of energy. So from this, remember N is equal to M on MR. You have energy here, and you're to calculate delta H for this equation. Don't forget to consider the coefficient. Come back and check the answer. Okay, hopefully you remembered to multiply your final answer by 2, add it to the end of the equation, and include the negative sign to state that the reaction is exothermic. So you should have ended up with a delta H is equal to minus 2610 kilojoules per mole for this question. Okay, so that's all the examples that we have. There are a number of other practice questions that you can use in your textbook. This is the bit where we need to be able to comfortably do experimental questions, questions from thermochemical equations, remember our conversions, and don't forget significant figures and units. I'll see you in class. Remember to bring your questions.